In the next few minutes, I'll show you what a vector database actually does, why a normal database can't handle similarity search at scale, what an approximate nearest neighbor index is, how the standard one called HNSW lets you search 100 million vectors in milliseconds, the one knob every team has to tune between speed and accuracy, and which of the dozen products in this space you should actually consider. Welcome to Concept Stack. We produce one concept a day, and each one stacks on the last, building the framework for AI together. Let's dive into vector databases. Last episode's RAG picture had a box in the middle labeled Vector Database. That's the box we opened today. Because the recipe sounds simple, embed every document, embed the user's question, return the closest chunks, until you actually have to do it. Imagine you've got 100 million chunks. Each one is 1,500 numbers long. The user types a question, and you have 100 or 200 milliseconds to find the 10 most similar chunks before they get bored. Comparing one vector to 100 million others, the obvious way, is wildly too slow. Here's the naive version. For every vector in your corpus, compute the cosine similarity to the query, then take the top 10. It's correct, it's also unusable. On a single CPU, comparing a query against 100 million 1,500 dimensional vectors takes about 30 seconds for one user per request, and you'd need 600 gigabytes of RAM to hold the corpus in memory. Run that math for 100 concurrent users, and the answer is a server farm to do something a phone should be able to do. So clearly, scanning every vector is not the move. We need an index. The whole field of vector search is built on one trade. It's called Approximate Nearest Neighbor, ANN for short. The idea is, instead of finding the exact 10 closest vectors, find 10 that are very probably in the closest 20 or 30. You give up a tiny amount of accuracy, and you get back 1,000 times speed up. The metric everyone reports is recall, the fraction of the true top K that your approximate search actually returned. A well-tuned index hits 95 to 99% recall while running in single-digit milliseconds. And honestly, for retrieval, missing one near tie almost never matters. The user can't tell. So basically, every production system uses ANN. The default index in basically every vector database is called HNSW, Hierarchical Navigable Small World. The name is dense. The idea isn't. You build a graph where each vector is a node, and each node is connected to a handful of its nearest neighbors. Then you stack layers on top, each one sparser than the last. The top layer has only a few dozen nodes, like express lanes between regions of the space. To search, you drop your query into the top layer, greedily hop to the node closest to it, drop down a layer, hop again, and so on. By the time you reach the bottom, dense layer, you're already in roughly the right neighborhood. For 100 million vectors, that's about 26 hops total, instead of 100 million comparisons. That's the whole trick. Every other algorithm in this space, IVF, product quantization, scalar quantization, is a variation on the same theme. Skip most of the comparisons. Once you're using HNSW, there's one knob you tune. It's called F-search, basically how many candidates the index keeps in play at each step of the walk. Crank it up and you check more options, get higher recall, and spend more milliseconds. Turn it down and you go faster, but miss more. The numbers shift with your data, but the shape is always the same. On 10 million vectors, you can hit 98% recall in 4 milliseconds, 99.6 in 12. The exact search baseline takes 8 seconds. Most teams land between 64 and 200. It's almost always the right pocket. This is the entire performance story. One knob, pick a point on the curve. In a real product, you almost never want pure vector similarity. You want similar documents that also belong to this customer's workspace, that are in English, that haven't been archived, that were updated this year. So every serious vector database lets you attach metadata to each vector and filter on it. The hard part is that filtering and ANN don't naturally compose. Some systems filter first, then run vector search on what's left. Fast when the filter is selective, slow when it isn't. Others run vector search first and filter the results. Fast usually, but if your filter is selective, you might come back with nothing. The good ones do something smarter, baking the filter into the index walk itself. When you're picking a vector database, This is the feature that quietly decides whether your queries take 5 milliseconds or 500. The market splits into 4 categories. Managed services, where you call an API and someone else runs the cluster. Pinecone is the best known, with Weaviate Cloud and newer entrants like TurboPuffer competing on price. Open source servers you run yourself. Quadrant, written in Rust, has become a favorite for raw speed and simple ops. Weaviate if you want a schema and a GraphQL API. Milvus if you're going to billions of vectors. Chroma if you want something that runs in your Python process while you prototype. Then there's the Just Use Postgres camp. The PG vector extension turns Postgres into a competent vector store, and your vectors live right next to the rest of your data. And finally, the libraries. PhiS from Meta and HNSW, which aren't databases at all, just an index you embed in your own service. Different shapes for different problems. If you only remember 2 options, remember these. At one end, you've got Pinecone, fully managed, serverless, scales to billions, but it's a separate system you talk to over the network and pay for by the read and by the stored vector. At the other end, you've got PG Vector, which is a tiny extension that turns the Postgres you're already running into a vector store. The huge advantage of PG Vector isn't speed. It's that your vectors live in the same database as your users. Your documents, your permissions, you can join them, you get real transactions. The rough rule of thumb is under about 10 million vectors, PG Vector is almost always enough and dramatically simpler. Past that, the dedicated systems start to pay for themselves. Most teams overestimate how many vectors they have. Start with PG Vector, switch if you actually outgrow it. 5 things that bite everyone. 1. Rebuilding the index is expensive. Adding a new metadata field, switching embedding models, growing past your shard size, any of those means re-embedding and re-indexing your whole corpus, and that can take hours. 2. Filter selectivity decides everything. A filter that matches 99% of your data is essentially free. A filter that matches 0.1% will quietly tank your latency unless your DB handles it well. 3. A vector database is not a real database. No joins, weak transactions. If 2 services need a consistent view of the same data, you'll feel it. 4. Hybrid search. The keyword plus semantic combo we covered last episode isn't built into every product. Some you bolt on. And 5. The one nobody wants to hear. Which vector database you pick matters less than how you chunk your documents in the first place. Bad chunks, fancy database, still bad results. Pullback in a vector database is honestly not that exotic. It's a specialized index optimized for one operation. Find the nearest neighbors of a vector, wrapped with metadata filtering and the usual machinery of a database. But it's the layer that turned embeddings from a research idea into infrastructure. Without it, every RAG app would take half a minute per query. Every more like this feature would need its own batch job. Every semantic search bar would just not exist. The stack we've built so far, tokens become embeddings, embeddings get stored in a vector database, is the input pipeline. It's how meaning gets into a form a model can use. Next, we go inside the model itself. That's the end of this concept, but each video stacks on the last. Subscribe and we add the next layer tomorrow. New videos every day on the AI concepts you keep hearing but nobody defines cleanly. Tomorrow, Transformers, the architecture that took everything we've stacked so far and turned it into the model. Thanks for watching.